The purpose of this lab is to analyze the projectile motion of an object by comparing real-world observations with model predictions, considering gravity and air resistance. Newton's second law states that the acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to its mass. The force of gravity formula follows the same structure as Newton's one, where g is the acceleration due to gravity, which usually is 9.8 meters per second squared in the negative y direction. The formula for drag force is represented by this formula, where b is a proportionality constant that's determined based on experimental data, v is the magnitude of the velocity, or better known as speed, and v hat is the unit vector of velocity corresponding to direction of motion. The negative sign indicates that force is in the opposite direction of motion. The total force acting on the object at that moment is the sum of gravity and drag. The velocity update formula uses the definition of acceleration from Newton's second law to update velocity over a small time step. Finally, to update the object's position, we assume that the velocity is constant over the small time step. The main results of this lab show that the computational model, only considering gravity, overpredicted the projectile significantly, and the model considering gravity and drag a little less compared to the real-life observations. For the experiment, I recorded a video of the motion of a ball thrown with a projectile motion. The video was analyzed in Tracker to extract the ball's motion data. Then, two computational models were constructed based on Newton's second law using a closed group. One model only includes the effect of gravity on the ball, and the other model includes the effects of both gravity and air resistance. Finally, the models were compared with the observations. The system is the ball and the surroundings or everything else around it, like air resistance in the ground. For the initial conditions of the experiment, I used the position and time from the first and second data points of the video to calculate the initial velocity of x and y components separately. As mentioned before, these are the initial conditions from the moment that I released the object. The b-value of the drag force formula was adjusted in closed group to follow the trajectory of the real-life observations as closely as possible. For each time step in this loop, the gravity and drag forces are calculated, then added to get the net force. The net force is used to update the velocity, and the velocity is used to update the position. That's how we get these predictions of the object's projectile motion. These lines control the arrows and visual representation of force and velocity vectors in the simulation. As seen in the output of the code for the first model, the cyan-colored arrow represents gravity pointing down, and the magenta one the velocity of the ball. The second model predicting the motion considering gravity and drag, the orange arrow represents the drag force, and the blue arrow, the blue ball, reaches the x-axis. The gravity and drag model, represented by the yellow line, closely matches the observed data in blue, up until the maximum height. After that, there's an increasing discrepancy between the two as the model overpredicts the height of the actual motion. Additionally, the general parabolic shape of the projectile motion is consistent across all the curves. The gravity-only model in red overestimates even more than the other model the height and the range of the projectile, which is expected since it doesn't account for air resistance and can travel farther. Overall, both models overpredict the distance in x and y traveled by the original data. Some sources of error could be the misalignment of the camera frame. The object also moved a little in the negative z direction, which isn't accounted for in the two-dimensional analysis done, and the b constant coefficient was determined through trial and error, so it might not be physically accurate. All of these could account for some error that may have distorted the track data. For the first part of the discussion, if the object were initially thrown straight up, all the initial velocity would be in the vertical direction. The object would go higher than the original case for the same initial speed, so it takes more time to come back down. For the second question, neither of the models predict terminal velocity. The experiment could be redesigned for the ball to be dropped from a greater height to give the object more time for air resistance to build up and balance the gravitational force. adding up to a net force of 0. Thank you for watching.